Okay, just to recap the program that we wrote last time, we had these blue dots as some data um, relating x and y, and we found using fitlm, this MATLAB command, um, the best fit straight line that captures this data, uh, minimizing uh, the mean squared error. And once you fit the best fit line, these yellow dots represent the error between the dots and the straight line. Okay. Now that's for this particular data set. And let's actually look at a different data set, which I have here, and run that. It's exactly the same process, exactly the same program. All I've done is change the data set. So the data looks like this, these blue dots, okay? And the best fit line does a reasonably good job, okay? It's not too bad, okay? And then we see the error looks like this. Maybe it's good to plot the error in a separate plot. Okay, so this is just the error. I suppose it sort of broke the legend here. Okay, so let's run that again. So we have two figures. One of them is the original plot with the data and the best fit straight line. And then the other plot is just the error, namely the difference between the raw data points and the straight line. And we can say x label, x, y label, error, or something like that, okay? Now, if you look at the error, you must notice something that is different from what you saw before for the previous data set. Okay, so let me just go back to the previous data set. That's the error. Okay, let me move my face down here. The error looks like that. The error seems to have no particular pattern. They are sort of randomly distributed about 0, it seems to me. That's for the first data set, where this straight line was doing a pretty good job. And then if you change the data set to this, now you see that the error, the difference between the data and the best fit straight line, seems to have some kind of a trend, if you will, right? So it seems to be it's not sort of randomly distributed, to sort of be informal here. Okay. Now, you can probably already see that sort of pattern in the original data set here, right? So the original data set feels like maybe it would be representable by a straight line, but maybe something nonlinear would be better. There's some curvature here that you can see, okay? So let's fit a nonlinear expression, okay? But using essentially the same procedure, right? So just because you're fitting a nonlinear function in some sense between the input and the output, it turns out that the same linear model fitting procedure works. You don't have to do anything different. Okay, so how do we do that? So it turns out that fitlm actually has some procedure, specific syntax for doing things like this. Actually, a couple of different syntaxes potentially. So if you go help fitlm, you can specify constant linear and squared terms by providing additional information like here, right? So by providing these additional inputs to fitlm. Okay, so but we are going to use sort of fitlm in a very naive manner for now. And in the initial sort of case, your input was X list, output was Y list, and then we just did fitlm input and output. Okay. Now what I'm going to do is, that's the linear model. Let's actually change that to a quadratic model. And then what I'm going to do is define this new variable called x input, and then go x list space, and then I'm going to give it another input, which is the square of x. Okay, so I'm going to say the inputs are x and x squared, and then what fitlm will try to do is try to find a model for y in terms of x and x squared. Okay, so that's one sort of simple way of using fitlm. But let's just do that. And then we will need to change a bunch of things here. So what I'm going to do is make this a separate cell. So as you may know, putting this double percentage sign makes these things separate cells. One advantage of our section, I guess in MATLAB terminology, one advantage of dividing these into sections is that you can run them one at a time. I'm going to run this section, run and advance, run and advance, run and advance. Okay, so I just ran this stuff. Of course, here I have not changed fitlm. It's still the same, so let's actually change that to x input. Now the input is now 2 columns. Let me run again. Okay, now let's type what the linear model is. Now the linear model now has 3 coefficients. This is the constant term, this is the x term, this is the x squared term. Okay. So this is the coefficient of the first input, this is the coefficient of the second input. In this case, the inputs are x and x squared, but it could be anything really. Okay. So this is one way of doing 2 inputs to this linear regression, where x1 is the first input, x2 is the second input. And this, in our case, it just happens that x1 is the x is the first input, x1, x squared is the second input, x2. Okay, so it says these are the coefficients. Okay, so let's actually, I have this program which I've called quadratic cubic polynomial. Let's actually just call it quadratic model or something, just to simplify things. Okay, so we've gotten that. So this is still the constant term. This is the linear term. And let's do B2 is the quadratic term. Okay, so more specifically, the coefficient of the quadratic term. And then we can plot the curve, the quadratic fit. So it's going to be b naught plus b1x plus b2x squared. And then we are just going to plot x versus y. And then we can compute the error. I'm going to comment that part out for now, so that we're not distracted by it. Okay, let's just run that thing. Okay. Was that better? Not sure. Okay. Let me make this LM quadratic here. Okay. And then it says press Shift Enter to rename all 4 instances. Let me do that. Let me just go LM linear, just so that we have a comparison here. Let's run the whole thing. Okay. I haven't changed any of the plots, but I have the linear model with the linear function as well. Okay, so if I go LM linear, which has just these 2 terms, the constant term and the linear term, the Root mean square error is 0.789. Okay, and then if I go LM quadratic, the root mean square error is 0.788. Okay, it's slightly better, barely better. Okay, so going from linear to quadratic did not decrease the error all that much. Um, let me just plot the error. That kind of a pattern still is there. Okay, in the error, there's some x dependence in the error. So which still suggests that we can add another term which has an x dependence to make the error basically be random, not really dependent on x, right? So eventually, we are trying to find y as a function of x, and once you fit this data, we would like ideally uh, the error term to not really have any obvious pattern with respect to x, right? So at least intuitively. Okay, so you may have noticed just by looking at the data that a quadratic model will not do very well. Okay, what does a quadratic model do? A quadratic model is basically just a parabola. It goes like this or like this. Those are the options, right? Y is the quadratic function of x will look like this or look like this. Clearly, this data set doesn't have a curvature just one way or another. It seems to curve one way and then the other way. Also, it sort of feels like it's an odd function, right? So it looks like it goes up, and then this is almost the negative of that. Okay, so it turns out perhaps looking at the data, you might infer that maybe a cubic model will do better. Okay, let's see if a cubic model does substantially better. And let me do that using a separate function, separate program. I'm just copying that, copy, paste. And then let me rename that cubic. Same data set, same initial scatter plot. And then of course, let's just do that. So now linear, quadratic, cubic. We can leave that in there, or for quadratic, maybe I can go x input. I'm just going to use, well, just to be consistent across the three lines, I'm going to say this LM cubic is basically x input, like it's a model from these three inputs to y. LM quadratic is basically, this is one column. Just okay, just so that you can see what this looks like, let me comment this out. Let me actually run this thing. Run, and then let me run that. What does x input look like? X input, it looks like three columns, right? So these are the three columns. The different inputs that determine the outputs are columns in this matrix. Okay, so for linear, I'm just going to use the first column. For quadratic, I'm just going to use the second column. And then for cubic, I'm going to use all the columns, right? So I'm just, actually, this is going to be first and the second column, not just the second column. First and second, we do that like this. And then here is just all the columns, no big deal. And this is not any longer true. I should probably fix that in this as well. Okay, so we have linear, quadratic, cubic. The reason why I'm also computing linear and quadratic is because I want to compare the root mean square error, just on, at least on the screen, but I'm just going to plot the cubic one. So exactly the same as before. Now we have another term. Let me just run these things one at a time now. Run, and then if I go LM cubic, it's got three terms because there are three inputs, and then this is the intercept term, which is the constant term. Okay, notice that the quadratic term is really small compared to the cubic term and the linear term, right? So there is a constant term, linear term, quadratic term is really small, cubic term. So that's exactly why when you tried a quadratic model, the fit was not much better than the linear model. Okay. Um, and then what's the R square value? The R square value is better. The root mean square is 0.7571. So let's actually look at that. Let me put my face out here. So LM linear, the root mean square error for the linear model is 0.789. For the cubic model, it's 0.571. It's much smaller, right? Like, I don't know. It's almost, I want to say 50% smaller, 40%ish. And then quadratic, we already saw, is just barely like 1/10 of a percent better than the linear model. Okay. Okay, so clearly the cubic model is better in terms of the root mean square error. Is it better in terms of what it looks like? So let's plot it. So we just pull out all the coefficients like so for convenience. I'm just, for these things, I'm not necessarily being the most efficient in terms of coding. I'm just trying to be pedagogical, which means like I'm trying to do the thing that would make things hopefully most clear. Okay. There are more efficient ways of doing these things. But okay, so this is the cubic term. More specifically, it's the coefficient, cubic coef of cubic term. I guess it would be the more precise thing to say, right? So let's say maybe precise things. And that's the constant. It's the coefficient of the constant term or just the constant, okay? Okay, so now plot the best fit line or best fit curve, if you want to call it that. X is the same thing. So we've actually made X list for the best fit line to go from the minimum X list, minimum value of X list to the maximum value of X list so that it covers the range of the data that we have, okay? And then we have B naught plus B1x plus B2x squared plus, what's it going to be? B3x cubed. Okay. This dot 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 allows me to continue a MATLAB sentence or a line of MATLAB onto the next line. Sometimes that's convenient rather than writing everything in the same line, or you can just put that like that. Doesn't matter. Okay. But in general, you don't want a line, a single line of MATLAB to go on and on off to the side. Okay. This should be good. Actually, the last time we computed error, there was a small mistake. I guess we have to change the error computation thing as well. Okay, so error list is going to be y list minus whatever is predicted by this expression, b naught plus b1x plus b2x squared plus b3x cubed. And then we can plot that, okay? But let me just comment that out anyway for now. Okay, let me run this section by section. Done, 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 done. Okay, so that's the curve. That's a nice best fit line. It looks pretty nice. It follows the data trend pretty well. And that sort of feels like that's the truth, right? So maybe you can go to a quartic model or a quintic model, but my guess is it will not improve things that much. Okay. Now there's a big caveat there. We'll spend a whole lecture talking about what that means. Okay, but Okay, let me just remove the error and plot it. Um, okay, so I don't know if you can see any pattern here. Perhaps not, perhaps. Um, Certainly feels much more random than before. We can certainly try a higher order model, like a quadratic model or a quintic model. Okay, maybe we can try that. Let's try that. So if you actually wanted to do that, there's actually a command called polyfit. But I'm not going to use that. I'm just going to use fitlm. There's like so many different ways of doing these fits in MATLAB. There's also a command called fit in MATLAB. Okay, but I'm just going to use fitlm because we're going to do the theory in a minute about how all these different things are basically doing the same calculations. Okay, so I'm just going to go polynomial model. Load data set. Maybe I'll fix an error while we are here. Quadratic model, I think when we did that here, I didn't say the error should be computed as. Like that. Okay. So we can run this again. This is the quadratic model. I missed that term because I left it as the same thing as what was in the linear model. Let's just run that thing. It's still there, right? So if you recall, this was the quadratic model, and there was this pattern that we saw. Okay. It's just a visualization of the error that was slightly wrong, but because the quadratic model was almost identical to the linear model, I think it didn't make a difference in our conclusions. Okay, so that's the linear and the quadratic and the cubic model. We can try to do a polynomial model, right? Okay, so let's do, how do we do this? Let's try to actually do the following thing where we systematically increase the degree of the polynomial. So let's go up till max degree of polynomial equal, let's go until 10, okay? And then do this thing over and over again for all 10 set of degrees, linear, quadratic, cubic, until 10th degree polynomials for, okay, I'm going to say I degree equals 1 to max degree of polynomial, okay? So I'm going to loop through the degree of polynomial, okay? I'm going to show what the fit looks like as we change the degree of polynomial. Now, for any given polynomial, we need to construct this matrix, right? So for second order polynomial or second degree polynomial, we need to construct a matrix that has these two columns. If you want a cubic polynomial, we need to construct something that has these three columns, etc., right? So how do we do that automatically? Well, we can do that automatically by doing another loop for I don't know. Unfortunately, it's again a degree. I term equals 1 to I degree. Oops, maybe not there. Okay, so here, what do I want to do? I want to maybe start x input equals some empty matrix. And then here I want to say x input equals x input space x list to the power I term. Okay, so when I term is 1, you will get x list. When I term is 2, it will get x list square. When I term is 3, x list cube, and so on. And as you run through this loop from 1 to I degree, this will obtain columns, I degree columns, which are x, x squared, x cubed until x to the power I degree, right? So we've assembled a matrix of the appropriate size. If you want to do fit a polynomial with I degree terms, then, or I degree nonlinear terms, or x dependent terms, you want this. Okay. And then here I'm just going to say, instead of LM cubic or linear, I'm just going to say LM polynomial equals x input, y input, exactly the same. Here, because we are now doing this over an indeterminate number of terms, depending on I degree, I don't want to actually hard code this, so let's actually just delete this whole thing. And then here, I'm going to compute y list. Y list for cubic, we just go in b naught plus b1 plus b2, etc. Rather, I'm going to, let me actually retain one of these lines because that's helpful. Let me just retain one of these things because I'm going to copy paste this. Okay. Okay, so here to actually compute this two lines, y as a function of x, we want to basically loop to compute the first term, the second term, the third term, fourth term, fifth term, sixth term, so on, depending on the length of the polynomial. So let me do this again, just like here. Let me go for I term equals 1 to I degree, and then I'm going to initialize y list as zeros of size of this. Okay, what does this mean? I'm going to initialize. So x list has 100 points between the minimum x list and the maximum x list, and then y list has just a bunch of zeros. But then I'm going to add to it all these terms. Okay. And basically, I'm going to add it like this. I'm going to say y list for best fit line is y list for best fit line plus dot dot dot. And then I'm going to go okay, so let me actually delete this thing for now. It's not that exciting. Okay, so the coefficient here is going to be, so let me actually do the following thing. Let me delete this. Let me clean this up a little bit. Okay. And let me run this. And I want to run it until this line, until you find the polynomial. So to do that, I'm going to actually put what's called a breakpoint right here. It will actually run the program until there. Okay. So just stop there, and it puts this k thing there. So it didn't run the whole program because we haven't written the whole program. This part of the program is sort of buggy and so on. We haven't even completed it, but we were able to run it until here. So let's look at what LM polynomial looks like. Okay, so of course the first term here is the constant term. The second coefficient is the linear term, etc. Right? So this is the constant term. Oops, not cubic. That's a constant term, that's a linear term, and so on. Okay, so what we want to do is basically, this is x. This is, I'm going to actually take the constant term and initialize y to the constant term. Okay, so initially y is just a constant term, and then I'm going to say for I term equals 1 to I degree, the degree of the polynomial, I'm going to say I term plus 1 is actually the coefficient. So for the linear term, for the x power 1 term, the coefficient is the second number. For the x power 2 term, it'll be the third number, and so on. So that's why it's I term plus 1 here. And then we go multiply x list power I term. Okay, just like here, right? So we are basically constructing here the prediction for y in terms of x from this polynomial model. We'll see how this thing works in a minute. So if this is not very clear, you will see how it's clear in a minute. And that's it. That should be it. So we loop through this to construct a prediction, and then we plot this, and then we put some legend there, and so on. Okay, let me put a pause here so that we can pause the program without it having to run the whole thing, without it running the whole thing, without our being able to see anything. Okay, so let me just run this thing. Maybe there's a bug here. Let's remove this breakpoint. Run it. There's a bug somewhere. Let's fix that. Aha. Okay, I meant to say here, size of x list, best fit line. Okay, it says undefined, unrecognized functional variable y list, of course. I wanted a list of ones, so if you don't know what this command means, this is basically a list of ones, but the list has exactly the same size as x list for best fit line. Okay, I'm constructing a list of ones and then multiplying by the constant term so that it's basically that list of constants. It's the same constant, b naught, b naught, b naught, b naught, b naught. Okay, I'm initializing it with b naught, and then I'm adding b1 times x, b2 times x squared, etc. So that's what's happening in this loop. Okay, so let's run this again and see what it looks like. Okay, another little bug. Okay, these bugs are great because we learn to do debugging here. Okay, okay. So I've used the variable lm cubic. No big deal. So I just because it's lm polynomial, we just fix that. Okay, so let's run this again. See if there are any other bugs. Okay, no bug. Okay, and it's paused, right? So paused, press any key. This is actually the linear fit to the data. It looks pretty similar to what we had before. Let me press enter so that it now moves to the quadratic fit. Okay, that's a quadratic fit. It basically writes it on top because it's the same. It's on hold on. Cubic fit looks much better. Okay, so before I move on, let me actually plot these things in maybe different plots. Let me Control C out, and let's put this stuff in here and go figure I degree so that the figure gets updated. Okay, let's run that. Linear, quadratic, cubic, quintic, looks pretty similar to cubic. Sorry, that was quartic, namely order 4. This is order 5. 6, 7 looks a little bit different. 8, 9 looks a little bit different. Maybe a little bit different. 10, okay. Okay, so that's how you fit higher and higher polynomials, okay? Um, let me stop the video there and show you a couple of post-processing things in the next video.